it's recording. So h, the number that we are subtracting from x, is what we call the horizontal displacement. So if h is positive, it goes to the right. If h is negative, it goes negative to the right, which just means to the left. Right, so if I do like absolute value of x minus 2, it's right there. If I do the absolute value of x plus 3, x minus negative 3 is the same as x plus 3, right? Look, it went to the left by a certain amount. Okay, by 3 in this case. All right, what happens if I multiply the whole function by a? So there's my parent graph. Right now, a is 1, so it's not doing anything. But what if I multiply by 2? What do you think that's going to do to the function? What do you think? How am I calculating these y values? Like if I plug in, look, we've got ordered pairs there. If I plug in 1 into my function, I'm getting 1 times the absolute value of 1, which is what? 1. If I plug in 2, I'm getting 1 times the absolute value of 2, which gives me 2. If I plug in negative 3, 1 times the absolute value of negative 3 is positive 3, right? Okay, what if I make a something other than 1, though? What if I made it 2? What's that doing to all of the y values that I'm calculating? It's going to, what's it going to do?
Multiply by 2.
It's going to multiply them by 2. So instead of going over 2 and up 2, I'm going to go over 2 and up how far? 4. Okay, so let's see what happens here. I'm going to go over 2 and up 4. Instead of going over 4 and up 4, I'm going to go over 4 and up 8. Okay, let's see if that works. If I let a equal 2. It does, right? So multiplying the function by a number stretches it, in this case, stretches it vertically. Okay, we call that a dilation. Remember the word dilation from geometry? What did it mean to get a dilation in geometry? Either like scaled it up or scaled it down, but everything stayed the same, right? If you dilate your eyes, what are you doing? Right? They're changing size, right? In this case, though, we have to be careful with this because this isn't a traditional dilation. This is only a vertical dilation. So all we're doing, it's like we're taking this, pretend that this whole plane is just made of like a rubber sheet. I'm just going to take the ends of the rubber sheet and I'm going to stretch it. Right? And I'm stretching the function with it. So I'm just dilating everything. I'm just changing. Does that make sense? It's like you can think of these points as being beads on vertical wires, and I'm just going to slide them up twice as tall as they used to be. Okay, but it doesn't stretch horizontally at all, only vertically. Okay? So what would happen if I made a 1/2 instead? What's that going to do? So comparing that to my original parent graph, instead of going over 2 and my normal height, when I move to the right by 2, my normal height is 2. What would my dilated height be if a was 1/2? It'd be 1, because I'm multiplying the result by 1/2. So I should expect it to be right there. What if I went over 4? Instead of going up 4, I'd go up 2. Okay, let's see if that works. Yeah, that works. Right? Okay, so we see something there. If a is a number bigger than 1, then it's going to stretch vertically, right? By a factor of a, whatever that is. I'm going to multiply all of the normal heights by a. If a is a number less than 1, then it's going to compress the function vertically because I'm multiplying the y values by a number smaller than 1, which makes them smaller, right? Okay? What if a is negative? What do you think that's going to do? So there a is 1. What if I made a negative 1? What do you think? What's that going to do to all the y values? Okay, I'm going to multiply, instead of going over 2 and up 2, now I'm going to go over 2 and up 2 times negative 1. Right? So over 2 and up 2 times negative 1 means I'm going up negative 2. So I'm going down 2. Instead of going over 4 and up 4, I'm going over 4 and up negative 4. You see that? Okay. Now, what if I combine the two things? What if A were like negative 3? What would happen? So if A were negative 3, instead of going over 2 and up 2, I'd go over 2 and up. Up is kind of tricky there. I'm going to go up 2 times negative 3, because I'm always multiplying that y value times the dilation factor. So I'm going up negative 6. What's that mean? Down 6. So I'd be going right there, right?
Oh, I get it.
Okay. Make sense?
Yeah, it does.
Okay, so then if we wanted to combine all this stuff, the final effect is, if we go down to the 5th link here, what this points out is that we can make any conceivable kind of absolute value graph by just simply tweaking those 3 parameters. Think of them like dials. We're just going to dial in values on those 3 parameters, and I can do anything I want to with this function, right? I can reflect it, I can squash it at the same time, I can slide it horizontally, I can slide it vertically, just depending on those 3 parameters. So then our goal is, by the end of the day, where we want to be with this is I want to be able to give you a function, and I want a transformation of some parent function, and I want you to be able to tell me what the graph's going to look like. And we can do that by just determining what are the values of each of those parameters and then making those changes to the function, tweaking it in that way. Okay? So let's fill in. Oh, did you get the notes, by the way? I don't think you did. Here's the. Come up and grab this real quick. You don't have this. Okay, so tell me what do these correspond to? Just fill in your notes as we go. This is the transformations guide, right? The part that's on the right. So if I have some parent graph f of x, and I'm adding a number to x inside the function, what's that going to do to the graph?
Move it left to right.
Okay, which way?
If you're adding a positive number, go to the right, wouldn't it? Or left.
And
sorry.
this is the one that's the opposite.
Yeah.
This is the one that's a little backwards. So this is the one where we're going to go left by h. Okay, it's going in the negative horizontal direction. Okay, h is for horizontal. So we end up with it's going to go left by h. What if I subtract some number from x inside the function? It goes right by h. Okay, those two are a little confusing. What if I add a number to the function? Up. So if I'm adding something outside the function, it goes up h. And if I subtract something outside the function, going down. If I multiply the function by some value of a where the size of the number is greater than 1. What'd that do? Like if we multiplied by 2 or by 3 or something, what'd it do?
It's like stretching the rubber shoulders made it skinnier.
Made it skinnier by stretching it up taller. Good. Okay, so we vertically stretch it. Oops.
Stretch it vertically.
By a factor of a. Factors are things we multiply by,
right, in math. We say factor, it means multiplication. So what if we're multiplying by a value of a whose value is less than 1? Like 1/2 or 1/4 or something like that.
Horizontally stretches by factor.
Okay, you could think of it as horizontally stretching, but technically speaking, we're vertically squashing in this case, or compressing. Vertically compressed by a factor of a. And then finally, what happens if I multiply a function by a negative number out front? What was the effect of that? Flipped it vertically, right? So it reflected it vertically. So then what we want to be able to do with this is if P of x is some parent graph, and I don't even know what it is. I don't even know, it could be an absolute value function, it might be a square root function, who knows? But regardless of what it is, I want you to be able to tell me here if f of x is what we call a transformation of P of x. Those three parameters we just talked about are the ways that we transform functions. So in math we call these transformations. I want you to tell me, how am I transforming P of x? Even though I don't know what it is, you can still tell me what's going on here by just identifying the values of those three parameters, a, h, and k. You can tell me what's going on. How are we tweaking this function? So first of all, what is a? So what is a? And you have to, this is called the process of inspection in math. We don't have to do anything. We just have to look at the function and compare it to our template. So where does a show up in any of these functions? What? No, a is always what's being multiplied out in front, so it's the coefficient of the function. So what's being multiplied out front? Negative 1/2. There you go. So a is negative 1/2. Okay, yes sir. Yep. We got to get h and k. Let's do k first because it's the easiest. K is pretty obvious. What's k? What is it? 3. Yeah, it's the number that's being added at the end, right outside of everything. So k is 3. Now what's h? You got to be careful with h. No. It's negative 4. Okay, now how come? Well, let's pause on that one for a second because that's the one that trips people up a little bit. Remember that h is always going to be defined as the number that's being subtracted from x inside the function. So if I have x plus 4 is equivalent to x minus what? X plus 4 equals x minus, no. X plus 4 equals x minus negative 4. Subtracting a negative is adding, isn't it? Right? See what I'm saying? That's tricky. But there's a little, you can make this simple though. You always know that whatever this operation is, inside the function, if you're adding, you're doing the opposite of what you think, right? If you're adding, you're actually, h is negative and you're going to the left. If you're subtracting a number from x, then h is positive and you're going to the right. Okay? But h is always defined as the number that's being subtracted from x, and so it's negative 4 here. So now you can tell me what's going on. H equals negative 4, what does that mean? What am I doing to the function because of that? I'm moving it right by negative 4, which means left 4. Okay, so this one's telling me left 4. What's k equals 3? Up 3. And there's two things going on here, right? A is negative, so it means I'm reflecting because it's negative. Reflecting vertically, and then what's that part doing? Compressing. By a factor of 1/2. Okay? So let's take another example. So what about something like this where I'm giving you a specific absolute value function, right? So now, what is the parent graph here? If I were to just get rid of all the numbers and make this the simplest possible example of that kind of function, what would it be? The parent graph. In other words, what's the parent graph that we're starting from scratch with here? Is it a square root? Is it a quadratic function? Is it an absolute value? What is it? Oh, okay. So what's the simplest absolute value function? Absolute value of? No, simpler. The parent graph, the very simplest one. Absolute value of x, yeah, right? So there's our parent graph, absolute value of x. Okay, but what are we doing to that? What are the values of a, h, and k? Because we've taken our simple parent graph, and we've developed something called f of x, which is a transformation of that. So we're subtracting h from x, and we're adding k, and we're multiplying by a, right? So there's our template. Okay? That's where the a and the h and the k would have to go if we were going to transform our parent graph, right? A is what's multiplied outside the function, h is what's subtracted from x, and k is what's added to the end, right? So based on our template then, what's the value of a? -1/5. So what's that mean? It's going to be compressed and reflected, okay? What's the value of h? 8? Positive or negative 8? 8. It's 8, isn't it? Because it's what's being subtracted from x. X minus h is being replaced by x minus 8. What'd I do? I just plugged in 8 for h, didn't I?
No.
Okay. And then finally, what's the number that's being added at the end? -2. So it's going to the right by 8, down by 2. Okay? Or, go ahead. Say it again.
The h always decides on.
Yeah, so the h is the horizontal translation, the k is the vertical translation, and a is the vertical dilation. Okay? So now, our goal now is we want to be able to come up with what is this graph based on that. That's a transformation of a real simple parent function. Okay, so we're going to do this two ways today, and this will be probably where we end today.
Oh, yeah. No?
Okay, so what's our parent graph here? Absolute value. Yeah, so we got an absolute value function. So P of x, I'm going to do this. So P of x equals absolute value of x. So let's always start with our parent graph, and then we'll just tweak it from there, right? Okay, so the absolute value function from yesterday, what is the graph of that parent function? What's it look like?
Absolute value?
Yeah.
Well, looks like a V.
Looks like a V, right? Where's the vertex of the V?
0.
0, 0, so at the origin. If I go over 1, I go up 1. If I go over 2, I go up 2. And then this is a function that has some helpful symmetry to us, right? It's got reflective symmetry about the y-axis. So symmetry is helpful in math. It allows us to cut our workload down a little bit. We can do half as much work essentially. If I know what the right side looks like, I can just reflect it over the y-axis to get the left side of the function also. So there's our parent graph. All right, so now we've got to do some stuff. Let's identify what are the values of the parameters here. What are the values of a, h, and k? So what's a? 3. What's h? What's k? -6. Okay, so now we've got 3 transformations to do, and we're going to do those in the order that the math gods dictate, and they do that with order of operations, right? These are just numbers that we're applying to our function, but there's an order that we have to follow when we do stuff to a function, right? It's PEMDAS.
Oh.
So the first step is going to be parentheses, right? If we're going to try to figure out what's going on here, we're going to try to to do all these things. We're multiplying by 3, we're subtracting 5 from x inside, and we're subtracting 6 from the function, right? What's the order in which we do those 3 operations? So what's the P stand for? Parentheses or grouping symbols of any kind. Good, so that'll be step 1. So which one, where up here do we see one of these parameters that's contained in grouping symbols? Which one? H, okay, good, because the H is inside, right? So there's our first step, is we've got to execute that change. So if H is 5, what does that mean we're doing to our parent graph first?
Going right by 5.
Going right by 5. H is the amount of the horizontal translation. So if it's positive 5, we're going in the positive, meaning the right direction, by 5. So the first step is everything's going to get slid over to there. Okay, so that's where the vertex is. The shape is still the same though, right? All we did was just slide it. Okay, now what's next? So next we go exponents. There are no exponents. Multiplication and division. You see some multiplication. The 3, so that's the A, isn't it? So that's the second thing we'd have to do for following order of operations, is we're going to do the dilation, 3. So what's that going to do now? Instead of going, like normally we would go over 2, and we're going to go up 2. But what we always do is we're always going to multiply the normal vertical distances by the dilation factor. So what are we multiplying by? By 3. So we're going to go up some distance. Three times 2, which is 6. Right? Make sense? So this point that used to be right here is going to get stretched up to right there, getting stretched up by a factor of 3. The point that used to be over 3 and up 3 is going to go up how far? That's going to go up to 9, isn't it? It's just going to go clear up there. And so we end up, point that used to be over 1 and up 1 is now up 3. And so you can see all those connect in a nice line, like they should. And then I can just reflect those over to get the points on the other side. So we've got 2 things done. We translated it horizontally and we stretched it vertically. What's the last thing to do? So that was step 2. Last thing is add or subtract. Outside of grouping symbols, right? So where's that? -6. So there's our third step. So what's that mean? If k is -6, what do I do? Going down 6. So that means this whole green shape up here is just going to get translated down intact, right? Doesn't get, we're only going to get slid. It's translation. It's going to get pushed down 6. And so the final shape just looks like that, doesn't it? Make sense?
Yeah.
Okay. So we had to draw. Now, what's the downside of this? I had to draw 1, 2, 3, 4 different shapes to get to the final one, right? I had to do all those transformations. So let's see if we can make this a little bit simpler here. If there's an easier process, and it's not always taught this way, but I think this is really helpful. I want you to notice a trend. What are the coordinates of the vertex?
Which one, the purple one?
Yeah.
6,
5, -6. Okay, there we go.
Oh my God.
Okay, would you notice those numbers anywhere?
Yeah.
Okay. Those are H and K. Is that an accident?
Whoa. Nothing in math's an accident.
Well, sometimes. But explain to me why that's not accidental, why we could have almost, well, in fact, we could have, not almost, we could have predicted that. How come? Where did the vertex start off? That's the key, isn't it? If it started off, think about that, if it started off at the origin, so both coordinates were 0, and I'm gonna slide this thing over by H horizontally and vertically by K, doesn't the vertex have to end up at HK every time? Right? Now, you might think, okay, here's the other part of that though. Is the dilation gonna mess that up? No, it's not, right? Because the dilation, here's how you think about the dilation. It's like we're gonna grab this thing by the vertex and drag it up. So the vertex always stays put, and we're gonna stretch it from the vertex. The height of the function, that's not a very mathematical term, so I gotta do my little air quotes when I do that. But the height of the function is really just the vertical distance of each point from the bottom, which is the vertex, right? So we could have done this a little easier, couldn't we? Couldn't we just have taken our parent graph and put the point that started at the origin, which is the vertex, put that at coordinates HK, and then from there, I could have just stretched up the shape by a factor of 3. A lot easier, isn't it? It's only 2 drawings instead of 4. So let's do the same problem. Let's just do it that way, just to show how much easier it is. You guys already told me, right? You already told me before. A is 3, and I'm going to write this differently this time. The ordered pair HK is just 5, -6, right? So we'll go over to 5, -6, and there's the vertex, right? And we don't even really probably have to graph this, but we'll just do it for now to make things a little bit more obvious. I'm going to graph the shape of the parent graph first. And then I'm just going to tweak that thing by dilating it by a factor of A, right? So if A is 3, we already did this step. If I normally would go over by 2 and up by 2, this time I'm going to go over by 2, and I'm going to go up by, oops, I went one too far, didn't I? And I'm going to go up by 3 times 2, which is 6. Everybody get that?
Yeah.
And so there's going to be my point. If I went over 2 and up 6, I can go back 2 and up 6. And much more easily, look at that, I got the final graph. Way easier, don't you think? Okay? So now you try one. Try that one. Here's graph paper. If you need graph paper, grab some, but try that real quick. That's our goal. If you can get this one today, we're in pretty good shape. Just a couple minutes, take a quick look. So what are the values of A, H, and K here? A is -2, and then let's write H and K as the coordinates of the vertex. What would they be? Okay, so the vertex is going to go back 6 and down 3, right? Okay, and then let's just think about what A is going to do. Normally, we'd go over 1 and up 1. Okay. Because it's what's being subtracted from X. Right? Remember, we're always replacing X minus H. What value would I plug in? If we start with X minus H, what value do I plug in for H to get X plus 6? I have to plug in -6. Right. Okay, so that one's always going to be the opposite of the sign. So now, if I normally go over 1 and up 1, this time I'm going to go up 1 times -2. So I'm going to go over 1 and down 2. And so all I really need is that point, don't I? Because then I can just reflect it over that axis of symmetry and get another point there. And look what we got. There's our shape. Okay.
See how
about it?
little lines there are? It's beautiful.
Yeah, it's nice. Okay, so last one, we're not going to do this one, but now think about this guy here. So look at the dilation part of this. Hold on 1 second for me, please. So if we're dilating this, if the dilation factor is -4/3, where's the we can do this quickly. Where's the vertex going to be? You can already tell me. -1, +2. So we know it's going to be right here, correct? Look how fast we can do this now. I want you to decide what's the most convenient point for us to tweak on the parent graph. We could go over 1 and up 1. We could go over 2 and up 2, over 3 and up 3, over 4 and up 4. So we're going up 1, 2, 3, or 4. Which one of those would be most convenient to multiply by -4/3? 4. Hold on. 3. Right? right? Because negative 4/3 times 3 would cancel the denominators, wouldn't it? I'd rather multiply by a number that's divisible by 3. So the one we're going to use is this one, right? So we're going to go, instead of going over 3 and up 3, we're going to go up 3 times 4/3. Well, what is negative 4/3 times 3 is what? Negative 4, right? So we're going to go over 3 and down 4. When we multiply the normal y value, the height, by the dilation factor, we get negative 4, and there it is. So we'll just reflect that point over. How fast is that? Okay, that was amazing. If I wouldn't break my expensive pen, I'd drop my pen.
Please excuse the interruption. When the bell rings, all students, please go to your advisory class.